Hello guys, and in this video I'm going to be talking about a class A amplifier. Let us consider it in the audio range of operation. A class A audio amplifier is essentially an amplifier which is commonly used because of its simplicity. It uses a single switching transistor in the standard common emitter circuit configuration to produce an inverted output. It is the most linear form of amplifier inherently. In this video I'm going to show you some calculations and formulas that you too can implement in designing your own class A audio amplifier for specific purposes. Without further ado, let me begin. I'm going to prepare my design on a breadboard so that it will be easy to move things around for experimenting before transferring it to a perf board. I chose a popular transistor to try out with so you are familiar with its good characteristics. Remember that a transistor is a linear device or very close to being perfectly linear. A transistor is an active element that needs a base voltage of 0.7 volts to turn on. And as you may know, most audio signal sources like your earphone sockets in your phones and other equipment are output audio has an output peak-to-peak voltage of 100 millivolts. Well, this isn't the voltage level for all low signal equipment, but almost any you can think of or have checked does not have a peak-to-peak voltage of 0.7 volts. But there are many devices that work up to that voltage range, but just in case. Now we need to bias the base to a voltage that will always keep it active without signal or with signal present. Let us call these resistors R1 and R2. If we assume a 1.2 volt peak to peak at their inputs, it will have 0.6 volt high and low swings. So a base voltage of 1.3 volt will suffice without any mistake or saturating the transistor. The formula will be VCC times R2 over R2 plus R1. The power supply voltage of my circuit will be 12 volts. Then we will have to access or randomly choose R2 and I choose 10 kilo ohms. Then rearranging the formula for getting R1, you get R1 equals to 12, which is the VCC times R2 over 1.3 all over minus 10. So the result leads to R1 being 82.3 kilo ohms, and the nearest standard value for 82.3 kilo ohms is 82 kilo ohms. Now we want our circuit to be exhibiting a voltage gain of 10, so we need an emitter resistor. To get our value for the emitter resistor, we use the formula, which is basically Ohm's law, but in terms of the emitter, where VE is the voltage across the emitter and IE is the current flowing through the emitter. To get the emitter voltage, we subtract 0.7 from the base bias voltage, which is 1.3. So we get a result of 0.6 if we subtract 0.7 from 1.3 volts. The current flowing through the emitter is the same current flowing through the collector, or very close to the current flowing through the collector. So for us to calculate the emitter resistor, we need more info. We need to know what you are going to be connecting at the output of the amp that you are making. So let's say we have a load impedance of 15 kilo ohms, so the collector resistor will be at this value. In class A BJT amplifier, we usually bias the collector to have a voltage of almost half of VCC. So in this case, it is 6 volts. Now the collector current will be still Ohm's law calculation, which is VC over RC, which will be 6 volts over 15,000 ohms, and it results to 0.4 milliamps. Since the current flowing through the emitter is the same flowing out of the collector, or very close to it, we can now calculate our emitter resistor. Now our emitter resistor will be RE equals to 0.6 volts over 0.4 mA, which gives us 1.5 kilo ohms. Note that thermal energy causes electrons to vibrate, and in the forward bias based emitter junction at a temperature of 25 degrees C. This creates a voltage of around 26 millivolts. This voltage sits on top of the emitter voltage inside the junction, so we can't measure it directly. Due to this, we have to calculate for another resistor to add up with the previous resistor we have calculated for the emitter to ensure overall stability. Doing this, we get 26 millivolts over the current flowing to the emitter, which is 26 millivolts over 0.4 milliamps. and the result came out as 65 ohms. Now adding this value with 1.5 kilo ohms will not be too bit of a difference, but the transistor knows itself best. Now that we have gotten the biasing resistors for the base, emitter and collector of the transistor, I think it is time we now calculate the impedance of the amplifier. The impedance of the amplifier's input is equal to the voltage divided resistors in parallel at the base of the transistor, which is in parallel with emitter resistor due to factors concerning the beta of a particular transistor. For small signal transistor like the 2N2222, we usually just use a value of beta equals to 100, unless you know that your transistor has significantly more or less gain. We can calculate the amplifier's input impedance as a parallel sum of 10 kilo ohms, 82 kilo ohms, and 150 kilo ohms in parallel, and the result is 8.413 kilo ohms. To find an input capacitor, we need a value that has an impedance a lot smaller than 8.413 kilo ohms, so as to allow almost all the input signal to appear at the amplifier's input. A good choice will be choosing a capacitor that has an impedance of 1/10 of the input impedance at the lowest frequency that we want to amplify. For audio, it is 20 Hz. We now have to calculate the capacitance that gives 841 ohms at 20 Hz, since capacitance is equal to inverse of 2 pi times frequency times resistance. Plugging the values into the formula, we get an answer of 9.46 microfarad. And since we may not find a standard value for that one, we choose an approximation of 10 microfarad, which should suffice. Now to calculate for the output capacitor. To get this, again, we need to calculate for a capacitor that is 1/10 the value of the collector resistor, so as to allow a lowest frequency of 20 Hz as a reactance of 1500 ohms. Well, this is all for this video. I am open to suggestions. In case you have any doubt or anything you know doesn't look or sound good, do not hesitate to comment in the comment section below. Thanks for watching and see you in the next video.